Hello and welcome to your physics online class. I am Mr. Marquez and today's topic continues to be discussing displacement with constant acceleration. Now in our previous videos we've talked about velocity, we talked about acceleration, and we defined acceleration basically as the change in velocity over a certain amount of time. Yesterday we spoke for the first time about velocity with constant acceleration, and we defined constant acceleration as a change in velocity every second over a certain amount of time. So basically acceleration is a change in velocity every second, and that can be positive acceleration if the velocity increases every second, or negative acceleration if the velocity decreases. Today we continue to talk about displacement with constant acceleration, but in a more specific way. Also, we're going to see the formula for velocity with constant acceleration. So let's go ahead and define that real quick. It says velocity with constant acceleration can be defined as velocity, final velocity, equals the initial velocity plus the acceleration multiplied by the change in time. And this equation is used to find final velocity after an object has accelerated for any time interval. So this is how we would find a final velocity after the acceleration remains constant, okay? Now here, we're going to talk about displacement with constant acceleration, which is kind of what we did yesterday, but this is more specific. And this is what I mean. It said displacement with constant acceleration can be defined as the change in x equals the initial velocity plus the change in time, or multiplied by the change in time, plus 1/2 of the acceleration multiplied by the change in time squared. So change in x equals the initial velocity multiplied by the change in time plus 1/2 of the acceleration multiplied by the change in time squared. And it says that it is used for finding displacement with constant acceleration, but for finding the required, it says it's used for finding displacement with constant acceleration, but more for finding the required velocity of an object to either reach a certain speed or come to a complete stop. So once again, it's used for finding the displacement of an object with constant acceleration, but it is also used for finding the specific acceleration in order for an object to move at a certain speed or come to a complete stop. Now, if we had to come to a complete stop, we would actually have to use both formulas. One to find the final velocity, and then the other one to find the displacement. But that's only when an object comes to a complete stop, which brings us to the problem. Now, this problem is found on page 53 of your textbooks, and it says a barge moving with a speed of 1 meter per second increases speed uniformly so that in 30 seconds it has traveled 60.2 meters. What is the magnitude of the barge's acceleration? So they're not asking us to find final velocity. In fact, the object is not coming to a complete stop, which means that we don't really need to use this formula, because if it had said that the barge came to a complete stop, then we would probably have our final velocity and we would need to find our initial velocity. But since they're not asking for that, in fact they're only giving us the initial velocity. And speaking of that, this is what I mean. So we're going to write down the information. We have the initial velocity, which is 1 meter per second. We have the change in time, which is 30 seconds. We have the change in x, which is 60.2 meters, and we're being asked to find the acceleration. Okay? So again, what I was saying is we're not going to use the final velocity formula because they're already giving up for two reasons. Number one, because it's saying that it's not saying that the barge is stopping. It's actually, or the problem is actually asking us to find the acceleration. So because the barge isn't stopping, we're not going to use the final velocity. And another reason is because they're giving us the initial velocity. If we had to find if we had to use this formula, the problem would have most likely given to us a final velocity, because if an object comes to a stop, the final velocity is 0. But since that's not the case, we're actually going to use this formula. Change in x equals the initial velocity multiplied by the change in time plus 1/2 of the acceleration multiplied by the change in time squared. So what we're going to do is just plug in our numbers and solve. You're obviously going to need a calculator for this because we are going to deal with extremely small numbers, so that is very useful. The change in x is 60.2. The initial velocity is 1. The change in time is 30 plus 1/2 of the acceleration, which is what we're looking for, and the change in time, which is 30 squared. So we're actually just going to kind of use our order of operations, and we're going to work with our parentheses and our exponents. So 30 squared is 900, so that means that this is plus 1/2 of the acceleration multiplied by 900 seconds. And 1 times 30 is 30, so we say 30, and 60.2, which we bring down, which is the change in x. So our next step is to actually get rid of this 30, and that way I can isolate this part of the equation. So you're going to subtract by 30 on both sides, and you're going to say 60.2 minus 30.0, if that makes it any easier. 2 minus 0 is 2, 60 minus 30 is 30, so that would be 30.2. This side cancels out. So now we're going to say 30.2 equals 1/2 of the acceleration multiplied by 900. So what I'm actually going to do is I'm going to erase this side of the board so we can continue the problem here, okay? That way the numbers don't look so scrunched up next to each other and it's easier to observe. So we have, and I'm writing it again, 30.2 equals 1/2 of the acceleration, multiplied by 900 seconds. So what we need to do now is we need to find the acceleration, but the way we do that is actually by dividing 900. And that's going to give you really small numbers, so that's why it's so important to use your calculator. So this side cancels out. 30.2 divided by 900 is approximately 0.035566 equals 1/2 times the acceleration. Okay? So you divide this in your calculator. This is more or less the approximate number that you're going to get. But now I have to divide that by 1/2. Now dividing it by 1/2 is the same thing as multiplying it by 2. So I'm going to invert my fraction, and this is actually going to be 2 over 1. And this is going to be 2 over 1 as well. And this side is going to cancel out, which means that my acceleration is, or I solve for acceleration. Basically, you're going to multiply 0.03556 times 2 and divide that by 1, and that would be 0.0671 approximately. And if we use scientific notation, ladies and gentlemen, which basically means that I'm going to write this in the form of m times n, 10, to the power of n. Let me write that better. I'm going to write it in scientific notation, which is again m times 10 to the power of n, where m is going to be the number and n is going to be the amount of times I remove the 0, the decimal place. Now, because the zeros are to the left, what I'm actually going to do is move this decimal point between the first two numbers. And you would say 1 and 2, and I would write that as 6.71, because since there's 2 zeros, it means I move by this once and twice, times 10. And because there are 2 zeros in front of this number, I say to the power of -2 meters per second squared equals it. Now, you don't have to express your answer in scientific notation. You don't have to express your answer in scientific notation. In fact, your calculator doesn't give it to you in scientific notation. But it's good that you review this because it is something that is very useful in physics and in other math classes. So again, guys, this is it for this video lesson. I want you to go to page 53 of your textbooks, and I want you to answer problems 1 through 3. And this has been your summer online physics class. Stay safe, and I'll see you guys very, very soon.